Some mathematical objects look simple at first glance. Just numbers arranged in a neat shape. Nothing extraordinary. But sometimes behind that simplicity lies a universe of patterns. A triangle that connects algebra, geometry, probability, fractals, and centuries of mathematical discovery. Today we're exploring one of those objects, Pascal's triangle. You have probably seen this triangle before. A triangular arrangement of numbers that almost looks like a simple pile of digits. But this is far from an ordinary triangle. In fact, it is a mathematical treasure chest. Different cultures have given this triangle different names. In India, it was known as the Steps of Mount Meru. In Iran, it is often called Khayyam's Triangle. In China, it appears as Yang Hui's triangle. Yet across most of the world, it is recognized as Pascal's triangle, named after the French mathematician Blaise Pascal. So the question is, what makes this triangle so important? In this video, we will explore some of the secrets hidden inside it. Let's begin with a brief explanation of how Pascal's triangle is constructed. This triangle is built from two main structural elements. First, it is made of horizontal rows. Each row sits beneath the previous one, and they continue downward without end, beginning from row 0 at the very top and extending toward infinity. Second, the triangle is also formed by diagonal lines. If you follow the numbers along these slanted parallel lines, you will notice that they create their own sequences. So this is not just a collection of rows. It is a structured diagram, a numerical construction, organized both horizontally and diagonally. The rows give it order. The diagonals give it pattern. And now that we understand how this structure is built, let's move to the first secret hidden inside this triangle. Now, let's move to the first secret of this triangle. The first secret is not hidden in complicated formulas. It is hidden in the structure itself. This triangle builds itself. Imagine placing an invisible 0 just outside the edges of every row. Now take any two adjacent numbers in a row and add them together. The result becomes the number directly beneath them in the next row. Each new row is created simply by adding neighboring numbers from the row above. And this process never stops. Row after row, the triangle grows downward, endlessly. That is the first secret. The triangle generates itself from a simple rule of addition. Now let's look a little deeper. Each row of Pascal's triangle is closely connected to something in algebra called a binomial expansion, which simply means expanding a power of a sum of two terms. In this connection, the number of the row tells us the power we are working with. And remember, the very top of the triangle is considered row 0. For example, when the power is 0, the expansion contains only one coefficient, 1. And that matches the top row of the triangle. When the power is 2, the expansion produces 3 coefficients, 1, 2, and 1. And these are exactly the numbers that appear in row 2 of Pascal's triangle. So Pascal's triangle is doing something remarkable. It gives us the coefficients of these expansions instantly. If you have the triangle, you can read the expansion. And if you know the expansion, you already know which row of the triangle it belongs to. Let's discover another pattern. Add the numbers in each row. 1, 2, 4, 8, and so on. Does this sequence look familiar? It is simply the powers of 2. Here is another fascinating observation. We can look at each row of Pascal's triangle and read its numbers as if they were digits forming a larger number. For example, consider the row that contains the numbers 1, 2, and 1. If we place these digits next to each other, we get the number 121. And interestingly, this number is the same as 11 multiplied by itself twice. Now, let's look at a deeper row. The one that contains the numbers 1, 6, 15, 20, 15, 6, and 1. If we carefully combine these numbers according to their positions, we obtain the number 1,771,561. And once again, this turns out to be 11 multiplied by itself 6 times. Now let's move into geometry. If you look carefully at Pascal's triangle, you will notice patterns running along its diagonals. The first diagonal is simple. It contains only ones. The second diagonal forms the counting numbers: 1, 2, 3, 4, 5, and so on. The third diagonal creates what mathematicians call triangular numbers. These are numbers like 1, 3, 6, 10, 15, and 21. Each of these numbers represents a collection of points that can be arranged into an equilateral triangle. Moving to the next diagonal, we encounter another sequence known as tetrahedral numbers. These numbers describe shapes in 3 dimensions. Structures built by stacking triangular layers on top of one another to form a pyramid-like solid called a tetrahedron. There is also something artists find especially fascinating. Pascal's triangle can generate a fractal known as the Sierpinski triangle. But what is a fractal? A fractal is a geometric structure where each part resembles the whole when magnified, a pattern of self-similarity. We see fractals everywhere in nature: leaves, coastlines, branching structures. Now here is the magic. If we color only the odd numbers in Pascal's triangle, a Sierpinski triangle suddenly appears. Mathematics becomes art. Now let's leave geometry and step into probability and combinatorics. Imagine a family with 5 children. What is the probability that exactly 3 of them are girls and 2 of them are boys? Each child has 2 possible outcomes: girl or boy. So for 5 children, the total number of possible outcomes is 2 multiplied by itself 5 times. That gives us 32 possible combinations. Now we ask, in how many of these outcomes do we have exactly 3 girls? The number of ways to choose 3 children out of 5 is 10. So the probability we are looking for is 10 out of 32. And now here is where Pascal's triangle appears. If we look at row 5 of the triangle, we see the numbers: 1, 5, 10, 10, 5, 1. That 10 in the middle is exactly the number we needed. Pascal's triangle was quietly giving us the answer all along. Let's try another example. Suppose we have a group of 12 people, and we want to select 5 of them. Instead of calculating everything from scratch, we can go directly to row 12 of Pascal's triangle. If we count from the left, starting at 0, and move to position 5, the number we find there gives us exactly the number of ways to choose 5 people from 12. Fast, visual, elegant. And this is only a glimpse of the patterns hidden inside Pascal's triangle. A simple arrangement of numbers, yet full of algebra, geometry, probability, fractals, and symmetry.